He's John Timpane.
And he's Don Rooney.
And this is
The Musical Innertube.
Now you may ask, why is this podcast called The Musical Innertube?
And we may reply, because that's its name, of course.
Now, how did this podcast get that name?
Back in college, we hosted a radio show. Once, we tried to introduce a soothing musical interlude.
Instead, we messed up and wound up introducing a soothing musical innertube, and the name stuck.
So here we are, hundreds of years later, still talking
to interesting people about their interesting lives.
Difference makers who really make a difference.
Today we're talking with David Wallace, who's both a philosopher and a physicist. David teaches at the University of Pittsburgh, where he holds the Mellon Chair in Philosophy of Science. He also has appointments in the Department of Philosophy and the Department of History and Philosophy of Science. Before coming to Pitt, he spent 22 years at the University of Oxford and 3 years at the University of Southern California. David says he likes cats and extinct dinosaurs, but doesn't currently own either. David, welcome to the Musical Innertube.
Great to be here.
David, we've asked you to be with us here today because it seems like popular culture has finally caught up with science. And by that I mean that in our popular culture now we have this multiverse or many worlds theory coming into like movies, for example. There's Everything Everywhere All at Once, which is an Oscar-nominated movie. And then there are movies with the Marvel characters, Doctor Strange, Spider-Man, where there are multiverses, other universes that do exactly what we do, except they're in a different level. They're in a different universe. But you say that there's actually some scientific background or some scientific theories that prove this, and you've been talking about it for a lot of your career. So could you clear this up a little bit for us? Tell us, what is the scientific basis for many worlds?
Sure. So the starting point here is a theory called quantum mechanics. And quantum mechanics is our best theory of the very small, but because big things are made of small things, it's really our best theory of essentially all of physics. It's predictive all the way down to the scales of finding the Higgs boson at the particle accelerator in CERN 10 years back, all the way up to predicting the structure of the night sky. In between, it explains your smartphone, it explains computers, it explains solid matter, it underpins nuclear weapons, for better or worse. It's been tested 1 million times, it passes these tests every time, it gets the result right sometimes to 10 decimal places. It's a good theory. But in some ways, it's a sort of scandalous theory because we don't really understand what it actually tells us about the world. You mentioned I like dinosaurs in your intro. We know about dinosaurs because we discover fossils. The point of the theory of dinosaurs isn't because we want to understand fossils. It's the other way around. We want to understand fossils because fossils tell us something about dinosaurs. We want to understand telescopes because telescopes tell us something about stars and planets. It's not the other way around. So likewise in quantum mechanics, we don't just want the theory to make good predictions. We want to say, what's it telling us about the systems it's describing? And if you try to understand that, you find yourself falling down a rabbit hole pretty fast. So just to cash that out a bit, quantum mechanics has a thing, well, the technical term is superposition principle, but I suppose you could call it the everything everywhere all at once principle in the modern popular culture. It basically says, if a system can have one property and it can have another property, it can have both at once. So if a particle can be here or there, it can be here and there at the same time. If it can be going this way or that way, it can be going this way and that way at the same time. And that's weird, but it's not just weird because the theory also seems to say that if we interact with those systems, those microscopic systems, then that everything everywhere all at once gets magnified up to our scales. So if I measure where the particle is and the particle is here and there at the same time, then my measurement says it's here and it's there at the same time. In the sort of famous, if scarcely ethical thought experiment for this, if I set things up so that if the particle's here, it kills my cat, and if my particle's there, it doesn't, then if the particle's here and there at the same time, after the measurement, the cat's alive and dead at the same time. And it doesn't seem like we see cats alive and dead at the same time. So normally what physicists do is just sort of, or have traditionally done, is kind of just hack the theory at that point and say, right, okay, stop using the theory to describe the world at this point, just like arbitrarily say, now we just understand the theory as describing observations. But if you actually try to genuinely make sense of what the theory's saying, then it seems like it's just saying something that either doesn't make any sense or isn't something we see. I mean, what would it be like to see a cat that's alive and dead at the same time? Your mental image is something like seeing double or being really drunk or something like that. So people have thought, okay, let's change the theory to fix that problem. The problem is, like I say, the theory works really, really well. People have said, let's drop the idea that the theory is supposed to describe the external world and just say, well, the theory is a gadget to make predictions. But as I said, that's not really very satisfying in terms of what we think scientific theories are for. And it also doesn't seem to connect to the fact that measurement devices don't work by magic. We seem to build them by physics principles. So what's the alternative? And that surprisingly leads us towards this idea of the multiverse. Because when you think really hard about what it would be like to see a cat that's alive and dead at the same time, you realize you can't trust your intuitions on that. You can't just say, what do I imagine straight off? Because intuition's a really bad way of discovering subatomic force. Yeah, exactly. It's almost the case, like if something seems intuitive in physics, it's probably wrong. So what we do is we ask the physics. Now, as far as the physics is concerned, I'm just one more physical system. And so my measuring something is governed by the rules of quantum physics. So what does quantum physics say? It says if I see a live cat, I go into a kind of mental state that you might describe as seeing a live cat. And if I see a dead cat, I go into some different mental state that you might describe as seeing a dead cat, and that'll show up in my neurons and the way what the things I'll say and so on. So according to the theory, if I see a cat that's alive and dead at the same time, then at the same time I go into a state of seeing a live cat and a state of seeing a dead cat. I definitely don't go into a state of seeing a weird indefinite cat. I somehow just go into these two perfectly ordinary states at the same time. And if you ask me on the podcast what happened to the cat, and I tell you, then you go into a state of hearing me saying it's alive and hearing me saying it's dead at the same time. And if your listeners want to know what happens to the cat, then they go into a state of hearing it being alive and hearing it dead at the same time. And all this stuff is correlated. So it's like the whole world is at the same time in a state of the cat being alive and everyone knowing it's alive, plus the cat being dead and everyone knowing it's dead. And those sort of two branches of what's going on are just separate aspects of what's going on. They don't interfere with each other. They don't interact with each other in any way. And so if you step back and say, what's that like? What would it be like if the world as a whole was at the same time doing two different things? Well, it's really just another way of saying, well, there's two worlds. There's two chunks of reality. Well, they're both quite ordinary. One of them is a chunk of reality with an Earth in which we see a live cat, and the other is a chunk of reality in which everyone's heard that there's a dead cat. So the idea of all of this, that's your multiverse. That's your branching into parallel worlds. But it's not something we decided to add to the physics. It's not something where we thought, oh my God, the physics is telling us terrible stuff. Let's fix the physics by adding parallel universes. That will be absurd. It's saying if we just sort of think really hard about the physics we actually have, then we realize all the way along, if we took it seriously, the physics was telling us that quantum mechanical measurements were branching reality into these separate worlds. Now, we don't, you can't be sure whether that's right necessarily. You could say, well, we haven't worked out, maybe the theory fails somewhere, maybe there's an error in the theory and the error somehow kills these worlds, but it is saying, if you do believe the theory and you take it seriously, it seems to be a multiverse theory.
The multiverse, it's interesting because the way you've just explained it, which is pellucid and I think compelling. People who don't like parallel worlds or the multiverse theory, I understand that they're slightly different, but and you know this better than I do, but they tend to be dismissive of it and say, well, it's sort of a trick that plugs some of our difficulties, but since we can't test for it, why should we even think about it? I'd like to talk about it. I mean, can we test for this? Is there ever going to be a situation where we can actually follow both branches as you've just described? Can you talk about that?
Yeah, absolutely. So it kind of depends a bit on what you mean by testing a theory. I mean, in practice, we always test theories against other theories. We have like alternate descriptions, and we see which fit better to the data. So the thing you can test in quantum mechanics, really, that all this rests on is it the case that whenever a system can have one property and another property, it can have both at once? So you can test this thing that physicists call the superposition principle. I was calling the everything everywhere all at once principle. And you can contextually try to test that for larger and larger systems. more and more complex systems. So we've tested that for, dawn of quantum mechanics, we were testing that for individual particles. We do these things called interference experiments, which basically are ways of getting, using the language of the multiverse, they're ways of getting one world to interfere and interact with another world. A thing called decoherence means in practice you can't do that on large scales, but you can do it on small scales. And you can try making the small scales bigger and bigger. So we did these interference experiments with particles back in the dawn of the theory. These days, we've done them with Buckminster Fullerene atoms. So these are things with like 300 individual subatomic constituents. I lose track of whether we've actually done it with bacteria yet, but if we haven't, we're not far off. We do it with kind of currents in quite large chunks of gear. We can push this principle outwards. And if it ever comes about that we push this principle outwards and it breaks, and we find, okay, when a system gets above a certain size or above a certain complexity, the superposition principle stops being true. In that case, the many worlds way of understanding quantum mechanics is dead. It's ruled out by experiment. So in that sense, it definitely speaks to experimental data. Could there ever directly be an experiment that checked not just for successively larger and larger bits of the superposition principle, but directly for the kind of, Dr. Strange level, different people having different thoughts and doing different things to different cats level? No, realistically never. There's not a barrier in principle in the physics to doing that, but there is a barrier in practice. But I mean, the way I like to analogize it too is the way we think about how we understand the night sky. So according to our best theories, then those lights in the sky are other suns, and even the lights in the sky we can't see except with really good telescopes. Those are distant galaxies. Those distant galaxies have billions of stars. Those stars have planets. Those planets have oceans. Those oceans have dust, have sand on the beaches. And we think those grains of sand are there because our theory says so. Now, we can test lots and lots and lots of predictions of our best theories of astrophysics and cosmology, but are we ever going to send anyone directly to that beach in this distant galaxy and check it's got sand on? No, definitely not. But we think we've got solid, not conclusive, but solid evidence that beach is there, because it's not something you can just excise from the theory, and the theory is super effective and super predictive. And that's how I think about the macroscopic scale, Earth scale branches in the many worlds theory. There's lots and lots of evidence for the smaller scale branchings. There's no principal barrier where it stops. We can't in any non-ad hoc way excise that stuff from the theory, so we should take them reasonably seriously.
What about the position of the observer? I've read where quantum mechanics will say that if a particle can exist in two places at once, it all depends on where you're looking at it, or which observer is looking at it from which angle. And so therefore, if it exists in two places at once, there could be two observers looking at it from different angles. How does that work into that?
Good. So you want to think about the many worlds approach in quantum mechanics as an alternative to giving the observer some really special status. So I was saying earlier, an observer is just a complicated physical system. I'm just a complicated physical system. In most of science, that would just be taken as common sense, but there are people in quantum mechanics who, since the beginning of the theory, have said, no, quantum mechanics is telling us observers are special. And I was talking about ways in which you could sort of modify the theory to get around this kind of live and dead at the same time cats. One way you can modify it is you can say, well, observers are special, and the way they're special is when observers interact with something that's doing two things at once, it suddenly stops doing two things at once and jumps into doing one thing at a time. So there's a quantum jump, collapse of the wave function. And it happens because observers are special. There's no physics reason it happens. It's just sort of, the magic of consciousness or something. And you can't really rule that kind of thing out remotely directly. I mean, maybe in science fictional situations where you can simulate the brain or something, but not in any remotely accessible period. So that could be right. But we don't seem to have any reason to think, this is contentious, I mean, philosophically, even religiously contentious, but scientifically, I don't think we have any reason to think that the human body isn't just some very complicated physical system and the laws of physics apply to it. The sense in which the many worlds theory is a quite conservative theory, that sounds weird given how bizarre it sounds, but it's what you get if you take rather conservative assumptions about the way science works and just apply them literally to quantum theory. There are less conservative moves you can make. Giving the observer a special status is definitely one of them. And if you give the observer a special status, then all of that branching, all of that everything everywhere all at once stops whenever someone looks at it.
So is it okay with you as a scientist that maybe you don't understand why I'm special, but you know that I am?
Well, I mean, we're special to us. We're special to ourselves, and
Of course.
Yeah.
and look, we're really good physical systems. We're terrific. I mean, human beings are easily the most complex, fascinating, difficult to understand physical systems in the entire known universe. Unless there are aliens out there, then there's nothing around more complex and difficult than us. I mean, I always say physics gets it easy. In physics, we study really simple systems like quarks and protons. The brain is ridiculous.
So I'm neurologists who have the really hard time.
Absolutely, yeah. So I'm not trying to do humans down here. But what, in big serious terms, what matters is all of that incredible complexity. Is that complexity ultimately the sort of emergent consequence of the fact that there are so many complicated moving parts in the brain? In which case, ultimately, the laws of physics still apply to it. Or does some actual magic occur that breaks the laws of physics? And that's the many worlds theory is what you get if you take quantum mechanics seriously and you don't put in the extra magic and you say humans are amazingly complex, but ultimately the laws of physics still apply to them.
Going back to what you were talking about, comparing it to the night sky and trying to figure out that planet billions of miles away that we will never get to, probably. I would think then, if we're talking about that kind of science and about the science that you've been talking about as far as quantum mechanics, that maybe the human brain, in trying to figure it out, goes on a fanciful sort of path and says, well, if this is the case, then we have multiverses. We have several thousand worlds that are parallel to ours with people exactly like us in them, and that they're doing exactly the same thing we are, or maybe they're doing something different. In other words, is it a way for the human brain to kind of cope with it by going out into those extended, fanciful, fictional regions almost?
I mean, look, this is a general question about how you want to understand scientific theories. I mean, there's a very austere position, you could say. Physicists sometimes call this shut up and calculate, where you just say, I'm just not going to say anything about what the theory means or says. I've learned how to do the math in grad school. I'm going to do the math. And then I'm going to ask the people who build particle accelerators to tell me if the math is confirmed. And you can do that. And there's nothing wrong with that. But none of it's denying the many worlds theory. It's just shutting up. If one actually wants to get understanding of what's going on, if he wants to, for instance, go on a popular podcast and answer questions about it in natural language, rather, I guess you don't want me just to put the Schrödinger equation up on my whiteboard and call it a day. then you end up having to give these kind of descriptions. And I mean, there's a sense in which all these things are a little bit fictitious. I mean, all the various things I've been describing to you are slightly imperfect paraphrases of the mathematics, but they get at the rough idea of what's going on. And if we want to take the theory seriously at all and describe in words what it tells us about the world, it's very hard to avoid this kind of talk of multiverses and branches and parallel goings on.
Now, one thing, just to follow on to this, something you said in one of your lectures that I thought was very interesting is it's probably true that physicists can't really express all they know in discursive language like we're using here on the podcast, because there's this imperfect overlay, to say the least, between the discursive language that comes out of our mouths and brains and symbolic language and math, which is the language of science. And we probably know more than we can say. So there's already a gap between those two languages. I love that notion.
Yeah, no, I think that's right. I think you said it very well. I mean, natural language is a great descriptive representational tool, but obviously the things it does best are the things it was evolved to do, which is describe, stuff on the surface of the earth, not too big, not too small, not too fast moving, or not too long time scales. When we start taking it outside those contexts, sometimes it stretches and tears a little bit. And mathematics has vastly expands our representational tools. It's a much richer, wider set of tools of which natural language is just a part. And particularly in something as abstract as physics, this is less true in the life sciences or something that's closer to the natural scale, but in fundamental physics, then we express things in the equations, and physicists talk about the equations all the time. They just mindlessly calculate, but the talk has a slightly metaphorical framework to it, and if you sort of really push people to be precise about it, at some point you get pushed back to the math. So I think it's always going to be true that our descriptions of what's going on have a slight fuzziness and a slight imperfection. I mean, that said, I don't think that's a huge problem from this point of view of the multiverse, because the individual worlds in the multiverse in quantum mechanics are, I was describing them in pretty ordinary everyday language. They've got cats in, they've got listeners to podcasts in, they've got the planets in. And the idea that the mathematics just represents multiple of these things simultaneously, I think that's a fairly literal transcription of what we're getting there. I mean, there are subtler things. If I ask you exactly how many of these branches there are, for instance, that's not really a very well-defined question. I mean, it's a big number, but it's a fuzzy number. It depends exactly how you define branches and exactly how different quantum mechanical stuff has to get before we say there's two branches rather than one. But I think I wouldn't want to think that the many worlds idea is just metaphor in that sense. It's again, if we should be taking the theory literally, if the theory is correct, then it is rather literally saying that elsewhere in physical reality there are other versions of me and other versions of you.
Now, going back to Schrodinger's cat, which we've been talking about, the one that's in the box and either alive or dead, or maybe alive and dead at the same time, that was always presented to me as a thought exercise. But was Schrodinger going for something more than that, or did that thought exercise then spring forth other people trying to develop it, or did it indeed suddenly come into development when the quantum physics came about? How did that all get together?
Good, yeah. So it was always a thought experiment. I mean, Schrodinger got up to some pretty bad things, unfortunately, but he never killed any cats. But the reason it's a thought experiment is because the actual experimental predictions are unambiguous. Nobody on any reading of quantum mechanics disagrees that what we'll write down in the lab book after the experiment is either I saw a live cat or I saw a dead cat, and then there'll be some. If you carry it out for hundreds of cats, let's just ramp up the ethical violation here. Then you'll find, like, depending how you set it up, maybe 50% of the cats are alive and 50% of the cats are dead. So the prediction's pretty solid. And the reason why there isn't anything very interesting about the prediction is because the cat's so big and complex, and because looking at it sort of spreads the multitude, the superposition to all of the sort of environment around the cat. There's no remotely plausible hope of taking the branch in which there's a live cat and the branch in which there's a dead cat and making them interfere with each other. But a lot of the name of the game in quantum experiments that are trying to push the frontiers here is how can you make the superposition more and more large and complex, not maybe as big as a cat, but something complicated with lots of moving parts. And yet nonetheless do that experiment that tells you, I didn't look, so I didn't collapse it into one thing or other. Instead, I let the two possibilities interfere, and then they did something that I couldn't have predicted on the assumption that it was either one or the other. I didn't know which. I mean, in a sense, this is what quantum computers are trying to do. The whole name of the game in building a quantum computer is to somehow allow the computer to be in a superposition of many, many, many different states, and yet to have that superposition remain confined to the box that the computer's in, so that it can do these interactions that nothing classical could ever do, and then spit out an answer at the end that relies on all of the terms in the superposition, all of the different ways the computer could have been, all the different worlds, if you like, and give us a result that we couldn't have done just by doing the calculation in one world.
I mean, it comes down to again, what we can actually talk about with our minds, which, as you've said, are the most complicated things that we've encountered in the universe. And, I was trying to explain to somebody one time that really quarks don't necessarily have to go from point A to point B in a line. Let's say they could take all possible roots and we'll just average them out. You'll get that line.
Yeah.
But it's not that we're saying we know how it got there. We know that it did. How it got there, we don't care how the car was driven. But for the purposes of the experiment, it seems to work well enough so that we know that it's a truth about the universe.
Yeah, absolutely. And then again, you can describe the way I describe that process in language, if I wanted to, as effectively the quark took all of those roots at once.
Right.
And some of them cancelled out and some of them reinforced. And the net result of all of that was the state of the quark we observe.
I went to a Denny's and had a cup of coffee. There's all sorts of possibilities. Right?
Yeah. And this is what I mean. So when I use, this is what goes back to your point about math. When I use many worlds language to describe the quark, I'm being a lot more metaphorical because we're down at the microscopic level here. And this language of worlds and branches works pretty well at the large scale macroscopic and only shakily well at the microscopic. I mean, I can write down the equation that we're describing in that language, but, and the description is really helpful. We give our students these verbal descriptions. No one can just take the uninterpreted mathematics and run with it. But the verbal description is fuzzy. It gets much better and sharper, oddly enough, when you get to this sort of macroscopic multiverse level where we're branching everything and where the interference between the branches that lets you detect it gets essentially invisible.
We'll return to our talk with David Wallace in just a moment. But first, here's a soothing musical interlude.
Besides teaching at the University of Pittsburgh, David Wallace also works with the Pittsburgh Quantum Institute. That's an organization that advances research, education, and training in quantum science and engineering.
David says he's been trying to develop and defend scientist Hugh Everett's interpretation of quantum theory, often called the many worlds interpretation. David's book on the Everett interpretation, The Emergent Multiverse, was published in June 2012 and is the joint winner of the 2013 Lakatos Award for Philosophy of Science. He's also written The Philosophy of Physics, a very short introduction.
To find out more about David Wallace, check out his University of Pittsburgh webpage. It's at hps.pitt.edu/people/David-Wallace.
And now, back to the musical Innertube, already in progress.
David, we all know that science is just all harmonious and wonderful and everybody agrees with everybody. and so that brings me to my next question, and that is, what kind of reaction are we getting to the theories that you're working on? How many people believe in it and work with you on it, and how many people say you are full of bunk?
Good. Yeah, I mean, this is. I mean, science is not harmonious at all. Generally, as a subject, there's this sort of beautiful, harmonious description that makes itself out in the popular science framework. But science is this kind of chaotic, often quite bad-tempered process with actual humans doing it. But I mean, the interpretation of quantum mechanics is a particularly sharp example of this. And okay, so lots of people in physics do what I previously described as shut up and calculate. They're not that concerned with how to interpret and understand the theory in these kind of contexts. They just want to get on and use it. And that's fine, to be honest. I wouldn't want to, it would be bad and unhelpful for everyone in physics to be dragged into the quantum measurement problem. Of people who want to understand it, very roughly, I'd say the many worlds theory is tied for first place among people's takes. It's not unpopular. I mean, lots of people will say it. Lots of physicists will say it's science fiction, but a lot of pretty serious physicists will say, yeah, I think this is the best way to think about it. I mean, Feynman did, for instance, depending how you read it. Hawking probably did. Ben Wilczek. It was a longish list. It gets a bit clearer, and this comes back to some of what we were saying earlier. If you say to physicists, what's the most helpful way to talk about theory, then a lot of them like this many worlds way of talking. If you say, do you believe in the many worlds, then people will start sort of, I'm not so sure, maybe I'm just a scientist, that's above my pay grade, all sorts of comments like that people go for. But yeah, no, it's It's contentious, but it's certainly not fringe. It's one of the more popular ways of thinking about quantum mechanics.
Well, it's very exciting, I must say. It's you can see why people would have disagreements. Let's just put it that way. I mean, it's probably good for science that they do. I mean, it's probably the juice, that keeps the car running in many ways.
Absolutely. No, I mean, we've learned a ton about the structure of quantum mechanics by thinking hard about these problems. I say we. Things I've done are very small contributions. So it should be, just in case it's completely clear, I did not come up with this idea. It's Patrick New Everett in the 50s. But yeah, I mean, if I think about how well we understood the structure of quantum mechanics and the physics of measurement and the physics of the classical quantum relation back in the 70s, and I compare it to how well we understand it now, there's just no comparison.
Now, you mentioned Dr. Everett came up with it in the 50s, but as I mentioned in the introduction, this is an idea anyway, that's been around for thousands of years, back to classical Greece and Rome, as I understand it.
Yeah, I think so. I mean, I'm very much a Philistine, non-historical, does the equations kind of guy, and my grasp of the detail of the history is not strong. I mean, in a sense, you can see, go back far enough, and there's not a really sharp distinction between this kind of multiverse and the idea just that, the stars have planets and planets could have people living on them. I mean, Giordano Bruno got burned at the stake for this. He was the guy who said maybe the stars are other suns, and the Catholic Church thought this is heretical because I don't know, was Jesus born on those other worlds or something? I'm not sure what their worry was, but that was a multiverse too. In a sense, astrophysics now is a multiverse. I mean, the other thing to say is this isn't the only place in modern science where you get the multiverse idea. So, if the cosmos is just physically much, much larger than the bit we can see, then you get some of the same things going on. So our current best theories of how the very early universe comes about has a thing called inflation, which basically says the very, very early universe just gets bigger and bigger exponentially fast. And in doing so, nearly all of the universe moves so far away from us that light from those parts of it won't reach us and will never reach us. So the bit of the universe we see in the sky is just this very, very small bit of what's really out there. And for various reasons, inflation's really hard to turn off. So once you start it, probably it keeps inflating somewhere. So you get a kind of multiverse in that sense as well. That's a different mechanism from the multiverse that gets delivered in quantum mechanics, but for different reasons, people in physics have been taking that idea quite seriously too. So you've got this sort of confluence of two different routes that lead you to the sort of same idea.
Well, it reminds me of a conversation I had with Jim Morrison years ago, where I asked him, so what do you think? We were talking about SETI, and I asked him, well, what do you think about the possibility of other worlds and other intelligent civilizations? And he said, well, I would say that the average for our galaxy alone is 1 in every 7,000 galaxies. And I said, well, what about outside? And he said, oh, well, the mind fails. Obviously, there are other, we know for one thing that there is no galactic empire because we would have heard from them by now. And the gates that are put on the speed of light, for example, mean that we will never contact, an infinite number almost of possible living intelligent forms. It leads to this sort of permanent frustration, I suppose.
Yeah, no, sure. I mean, the galactic empire point, well taken. I mean, sometimes this gets called the Fermi paradox.
Right.
The galaxy is really big, but it's much older than it's big. The galaxy, at the speed of light, it would take you about 100,000 years to cross the galaxy, but the galaxy has been there 10,000 million years. So light could have crossed the galaxy, where are we, like 100,000 times or something, in the time it's been around. I've done that at the top of my head, I put the math wrong, but anyway, a lot of times.
Yes.
So, and even much, much slower moving space probes could have done it. So the fact that that there's no evidence in the Milky Way that seems to contradict the idea it's all natural is some reason to think at least that alien life is not super common. Maybe more than that. And yeah, I mean, and I think it's, in a sense, this is the kind of reason why I don't get too worried about the apparently kind of extraordinary scale of something like the many worlds theory. I mean, when you sort of just think deeply about our ordinary astrophysics and the size of the galaxy and the size of the observable universe and how old it is, it's like, it sort of blows your mind. I mean, I know I can't clearly get into my own mind, to be honest, how far it is to the moon.
Yes.
I could give you the numbers for that perfectly happily, but if you ask, can I really intuitively grasp it? I don't think I can. And that's a ridiculously small distance compared to the sort of distance to the center of the galaxy or something.
How far along are we in our understanding of this? I'm sure that we can go way, way deeper, but do we have a grasp of it, or are we still trying to get a grasp of it? And if so, how tenuous is that grasp?
So I think we have a fairly solid grasp, to be honest. I mean, the basic underlying theory here, quantum theory, is 100 years old. It's mathematically understood pretty well. The thing to understand about it, it's a framework in which you can write more specific theories. So if you ask, what should our fundamental theory of physics be? Maybe it's string theory or something else at the incredibly small scale. All of that stuff's incredibly speculative. We don't at all know what that theory should be. But the many worlds stuff is not a consequence of our most fundamental physics. It's a playing out of quantum theory at whatever scale, and we understand sort of atomic and subatomic scale physics pretty well. And in the last 50 years, we've got a reasonably solid handle on the way in which quantum superpositions get sort of fuzzed out and the way in which this branch language can be used and described. So there's lots more to explore and understand there. But I think we're very much at the level at which this is a way of thinking and talking about quantum mechanics that lets us keep doing quantum mechanics and keep developing the specific sciences. It's not a place, I think, where there are, other than the strangeness of it, where there are just abiding scientific mysteries. I mean, there are lots and lots of deep philosophical questions it throws up about how the truth of the many worlds theory would change all manner of our ideas, from philosophy of religion, of language, of metaphysics, of morality. But internal to the physics, I'd say we have a reasonably secure grip of what's going on.
I'd be very interested now to go to one of these other worlds and see how this interview went between the three of us in another world. David Wallace, thanks very much for being with us.
So very much, yes.
Thanks for having me.
And thank you for listening to the Musical Innertube.
The Musical Innertube is available everywhere good podcasts are found. Listen on your favorite platform and give us a good rating.
You can subscribe to the podcast on our website, musicalinnertube.com.
There you can listen to all of our podcasts, see pictures and biographies of our guests, and contact us. You could even leave us a voicemail.
And don't forget to leave your email address on our Talk to the Two page on the website, and we'll send you a preview of who's coming to talk with us by email, just so you're prepared.
That's musicalinnertube.com.
And as always, thanks to virtual band Car Radio Dog for our theme music.